This video will explain concurrency control. Concurrency control is about managing simultaneous access to data in operating systems. Concurrency is the ability of different parts or units of a program, algorithm, or system to be executed out of order or in partial order, without affecting the final outcome. In simpler terms, it is when multiple processes or threads access and manipulate shared resources simultaneously. The diagram shown depicts multiple processes trying to access the database at the same time. Concurrency control is needed to avoid certain problems. One is a race condition. When multiple processes access and manipulate shared data concurrently, the outcome depends on the particular order of execution. Look at the code snippet shown. Process 1 gets the balance, which is $1,000, and tries to increment it by $100. Process 2 at the same time gets the balance, which is still $1,000, and tries to deduct $50 from it. Without proper controls, concurrent operations can lead to data inconsistency, such as lost updates, inconsistent retrievals, unrepeatable reads, and phantom reads. The final balance becomes $950 instead of the correct $1,050. The critical section is a segment of code where processes access and manipulate shared resources. This section must not be executed by more than one process at a time. Any solution to the critical section problem must satisfy these three requirements. First, mutual exclusion, where only one process can execute in the critical section at a time. Second, progress. If no process is in the critical section, a process that wants to enter must be allowed to do so. Third, bounded waiting, where a process waiting to enter its critical section must eventually be allowed to do so. The diagram on the right shows the critical section. Only one process can be in the critical section at any given moment, hence a lock is needed. Processes enter the entry section before accessing the critical section, and then exit through the exit section. A lock is a synchronization mechanism that restricts access to a shared resource to only one process at a time. The code snippet shown is an example of a lock. The lock is initially set to false, indicating that it is unlocked. A process wanting to enter a critical section first calls the acquire lock function. This function continuously checks if the lock is currently true. If it is true, the process waits until the lock becomes available, which means that it becomes false. Once the lock becomes available, the process acquires the lock and sets it to true. After executing the critical section code, the process calls the release lock function, which sets the lock back to false, allowing another process to acquire it. There are various types of locks, such as spin locks, mutexes, semaphores, read-write locks, and recursive locks. A semaphore is a variable that controls access to a shared resource through the use of two atomic operations: wait, also known as P, and signal, also known as V. The code snippet shown gives an example of semaphore implementation. Here, semaphore is initialized to 1 representing a binary semaphore. The wait operation continuously checks if the semaphore value is less than or equal to 0. If it is, the process waits. Otherwise, it decrements the semaphore value. The signal operation increments the semaphore value, potentially allowing a waiting process to proceed. There are two types of semaphores. A binary semaphore can only take values 0 or 1, similar to a mutex. A counting semaphore can take arbitrary non-negative values. Semaphores are commonly used for controlling access to a shared resource, signaling between threads or processes, and implementing producer-consumer scenarios. A monitor is a high-level synchronization construct that encapsulates shared data variables, procedures that operate on the shared data, and synchronization between concurrent processes. The diagram shown depicts this encapsulation, with the monitor containing shared data, operations, and condition variables. Several processes are requesting to access the monitor. There is also an entry queue where processes wait to enter the monitor. Monitors offer several advantages, including encapsulation of data and operations, automatic mutual exclusion, condition variables for process coordination, a higher level abstraction than semaphores, and reduce susceptibility to programming errors. A deadlock occurs when two or more processes are waiting indefinitely for an event that can only be caused by one of the waiting processes. Each process is waiting for a resource that is held by another process, creating a circular wait condition. There are four necessary conditions for deadlock. Mutual exclusion: at least one resource must be held in a non-shareable mode. Hold and wait: a process holding resources can request more resources. No preemption: resources cannot be forcibly taken from a process. And circular wait: a circular chain of processes, each waiting for a resource held by the next process. The diagram shows the circular wait condition for a deadlock. Processes P1, P2, P3, and P4 are waiting for resources held by other processes in a circular manner, resulting in a deadlock. There are four main strategies for handling deadlocks. First, deadlock prevention ensures that at least one of the necessary conditions for deadlock cannot hold. This involves eliminating mutual exclusion when possible, preventing hold and wait by requesting all resources at once, allowing preemption of resources, and preventing circular wait by imposing resource ordering. Second, deadlock avoidance dynamically examines resource allocation to ensure the system never enters an unsafe state. This requires advanced knowledge of resource needs. The banker's algorithm ensures the system remains in a safe state, but it is a conservative approach that may deny requests even if no deadlock would occur. Third, deadlock detection allows deadlocks to occur, but implements a detection algorithm to identify them. This includes using a resource allocation graph, a wait for graph, and periodic execution of a detection algorithm. Fourth, deadlock recovery: once a deadlock is detected, breaks it by forcibly taking resources or terminating processes. This involves process termination, killing one or all deadlock processes, resource preemption, temporarily taking resources away, and rollback to a safe checkpoint. To summarize, concurrency enables multiple processes to execute simultaneously. Critical sections must be protected to maintain data integrity. Synchronization mechanisms prevent race conditions. Deadlocks occur when processes are waiting indefinitely for each other. Challenges in concurrency include balancing performance with correctness, avoiding deadlocks and livelocks, minimizing overhead of synchronization, and ensuring fairness in resource allocation. The most important synchronization mechanisms include locks, which are a basic mechanism for mutual exclusion, semaphores, which are a signaling mechanism that can control access to multiple resources, monitors, which are a high-level construct that encapsulates data with procedures that provide synchronized access, condition variables, which allow threads to wait for specific conditions before proceeding, and message passing, which is communication-based synchronization where processes exchange messages. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.